Hello, this talk is about package management in the Julia programming language. Here is what I'm going to cover today. By the end of the talk, you will see how Julia's package management system works and how to use it to your advantage for your research and code development. In terms of using Julia, some of us might be just users who use available packages to do our computations. Or maybe you are developing your software package written in Julia that eventually you want to publish and share with others. This talk will cover both situations in terms of package management in Julia. The talk has two parts. In the first part, I will talk about the package managers in general. They can be loosely divided into two types. One is at the operating system level. The other one is at the user space level. One can argue that there is a third type that is sitting in between, the hybrid. Here, by user space, I mean a place a user can install programs or data without system administrator's privilege. The reason to talk about all these other systems is to bring out their usefulness and limitations. Later in the talk, we will see the Julia approach to address these issues, in particular the limitations by these other systems. In the second part of the talk, I will talk about the Julia's package manager itself, or the PKG. There are different components involved, including the location of the binary Julia installation that is separate from the Julia repository in your home directory, and that is also separate from your other folders containing your Julia code or projects. This is not as complicated as it sounds. We will first take an overview of the whole thing, then I will go into the individual components and explain how it works. We will talk about how to manage multiple environments. If you are a Python user, you know about the virtual environment. If you are an R user, you know about the R environment tool. I think you will see that the Julia's approach is a bit more consistent and elegant than these other systems. At the end, we will talk about how to package your code to share with others. This is useful. For example, when you publish your paper and your code, others can download your code and run in the exactly same state as yours. In fact, even if you don't share your code with others, the PKG mechanism will help you to run your code in the exact same state, say a year later, even if a bunch of packages in the system have been upgraded. If you have tried this before, you will see that it is not always easy. Actually, it is almost always not easy. This can be easily achieved by Julia's package system because of its design. In my opinion, it is one of the good approaches to achieve reproducible computation or research without too much trouble. I want to point out that using version control alone may not be enough to achieve this. This is because scientific computations often involve more than just the code itself. We will explain more about this later in the talk. Here are some examples of the operating system level package managers. On the left is the Microsoft system, and this is a built-in package management in Microsoft system where we can easily add or delete packages. Mac has a similar setup. So in this Mac OS, you can easily delete or add applications supported by the Mac OS systems. Linux system has different flavors or distributions, and each distribution uses its own package managers. For example, Ubuntu and Debian, they use the APT ones, and others use RPM or Yum or Pacman. On the bottom here, I also added some third-party package managers for Windows and for Mac OS. And Linux system, the package managers are pretty good. So normally you don't need another third-party package managers for Linux system. I just want to put this picture out there as a reference for our later discussion about package dependencies. Here are some of the examples in terms of the user space package managers. And the examples here are data science oriented. One of the popular package manager for data science related packages is the Conda system. And this system can manage packages not only for Python, but also for several other languages. There is also RStudio package management, but this is not free. And this is from their website, it says that it can manage packages for R and Python. There is also an Enthought deployment manager that is similar to the Conda system that manages Python and several other packages. Here I put two kind of related product. One is VirtualBox and one is Docker. They are not package managers per se, but there are some packages these days. They are distributed either as a virtual machine or as a container, and so that's why I mentioned them here. So all of this usually operate in the user space. The general observation here is that the OS level package managers, they focus on non-scientific computing aspects of computer usage, and usually they require system administrator privilege. On the other hand, the user space package managers, they can fill the gap by providing scientific computing specific packages. Some of the package managers we saw in the previous slides, they focus on certain domains, for example, data science and biological computing. I'm going to make some comments about existing package managers for Python and R and talk about their pros and cons. From a user's point of view, there are clear advantages of using a package manager. The package installation process is much more simplified when a package manager is used. When a package is installed, the compatible dependencies are also automatically installed, and the package is ready to run. It is also easy to keep the packages up to date by synchronizing with some central database. However, there are some drawbacks for some of these package managers. First, for historical reasons, the package management is an afterthought after the package was invented and is external to the language itself. Therefore, it is common that a computer system uses more than one package manager to manage the packages. This results in inconsistent installation locations of the install packages. This can cause confusion or failure to run. Second, since the runtime system can load only one virtual environment at a time, the package that may need to be installed may have to be duplicated across the virtual environments in order to make each environment to work. Third, it is a non-trivial process to package a user's program for distribution. Each of the different package management system uses different mechanism to package the user program for distribution. Of course, like I said earlier, some of these are caused by historical reasons. It is not somebody's fault. In the rest of the talk, we will see how Julia's package system addresses these problems. You will see that while Python and R use some specific special mechanism to maintain the packages, Julia used the most popular Git version control system to manage its packages, both at the local level and at the remote servers. After looking at the OS level package managers and other package managers in the user space, now we turn to the Julia language. Just a brief introduction of the Julia language. So Julia first appeared in 2012. I think the project started in 2008 or 2009. It first released in 2012. And the initial 4 developers, they are the authors of these 2 famous articles. They wanted the language to be open sourced, and it has as good as MATLAB, Python, R, Perl, MATLAB, and Shell, and as fast as C. So you see that they want to combine all of the advantage of all of these well-established languages. And if you are interested, you should go back to these 2 articles. The first one is published in 2012 as a Brock article by these 4 initial developers of Julia language. And the title is Why We Created Julia. And there the authors listed their reason to create a new language and also what they wanted from this new language. A few years later, another article appeared in the archive. So this is a Julia, a fresh approach to numerical computing, also authored by these 4 authors. And here is also an extensive discussion of what the language features they are designing or they were designing at that time. Fast forward to now. So in 2018, Julia 1.0 was released. The version 1.0 signifies that the language has reached a certain mature level, ready for production use. In 2019, the authors received 2 prestigious prizes. One is the Wilkinson Prize for Numerical Software. This is a prize that is only awarded every 4 years. So you can see the quality of the software or the language confirmed by the research and the computing community. There are 2 ways to access Julia's package manager, the PKG. PKG is part of Julia's standard library. It is installed when you install Julia. PKG has undergone significant changes recently. It is recommended that you install the latest Julia version to get the latest functionality of PKG and the rest of Julia system. The latest Julia version is 1.6 at this time. The first approach here is to access PKG inside the Julia code, just like any other Julia's modules in the Julia code. This is suitable for scripted installation. For example, if you want to duplicate the installation of the exact sequence of packages, this is a way to go. Or if you want to share the installation sequence with someone else, this is a good approach. The second approach, which is what I'm going to show you in a little bit, is to use the PKG mode in the Julia repo. Julia repo is the Julia interactive command prompt. Compared to other scripting languages' interactive command prompt, Julia's repo is quite advanced and convenient. Let's see it. Here is a little demo of how Julia Package Manager inside the repo looks like. So for my terminal here, I type the Julia command and I enter the Julia repo, the Julia interactive command prompt. So here you see the Julia logo in text mode, and also you see the Julia version number 1.6.1 corresponding to my installation of Julia, and this is the release date of this particular version. And here we see the Julia command prompt, Julia greater than sign. So at this point, we are ready to enter some Julia code to run. But this is not what we are going to do here. So here we are going to look at the Julia Package Management System, the PKG. So if you are going to forget about the command I'm going to tell you here, there is a little hint here when you enter Julia system. So here, if you type the question mark in the Julia command prompt, you are going to get the Julia help system. If you enter square bracket followed by the question mark, then you are going to get the Julia help system for the package manager. So to enter the Julia package manager mode, the PKG mode, you simply press the square bracket key. You cannot see my keyboard here, but if you press the square bracket key, you will see that the command prompt instantly changed to this PKG command prompt, meaning that we are now in the package management mode. The version number, version 1.6 here, indicates that this is the package management corresponding to my Julia installation 1.6 series. So this is consistent with my version number displayed here. So from the package mode command prompt to go back to the interactive Julia command prompt, you simply press the backspace. You press the backspace once, you go back to the Julia command prompt. So now we are in the normal Julia mode. And to go back to the PKG mode, you press the square bracket, and then you go back to the PKG mode. So you can easily go in back and forth between the interactive Julia command prompt and the PKG mode, back and forth depending on what you need. So suppose we are inside the package mode, and we want to do some package inspection or manipulation. One thing you can do is that to list all of the packages installed in this environment. So the command to do that is to see is status. So status will display the packages installed in my current Julia environment. So there are only 2 packages here. So these are the 2 packages that are installed on top of my default Julia system. So these are 2 externally installed packages. They are not part of the default Julia system. But in fact, when you install a package like this, this tool, in addition to these 2 packages, these 2 packages also carry their dependencies. So the installation of these 2 packages will also trigger installation of other dependent packages. To see those dependent packages, in addition to the status command, we have to add this -- manifest option. So when you do this, you will see a long list of packages. So let's scroll back. So we type this status manifest command. You will see that these 2 packages, in addition to these 2 packages, for example, data frames is here. In addition to these 2, there are many other packages. So the format is always the package name followed by the version numbers. And there is a kind of mysterious hash code that we will talk about later. So manifest is the way to see all of the packages, including those dependency packages. And also the other thing to notice is that the format here is the package name followed by the version numbers. But if you scroll down a little bit, you will see that there are a bunch of packages without the version numbers. So this means that these packages without the version numbers, they are part of the Julia built-in default packages. So they are Julia's standard libraries. Right, so that's how the display is organized. And if you go back to our earlier part, you also see these 2 special files. So when you run status command, we see this project.toml file. When we run status manifest, we see this manifest.toml files. So we will talk about these 2 files in more details later in the presentation. So this is what Julia's package management system inside the Julia repo looks like. So now from the command prompt, you know that we are still in the package mode. And to go back to the Julia normal command prompt, we just press the backspace key. And now we are back to the Julia normal command prompt. Here is another demo to see the process of package installation. So now inside the Julia command prompt, I enter the package mode and I do the status to see that this is an empty project. Now I install the CSV package by using the add command. It downloads all the dependency packages and then it starts to compile because again Julia is a compiled language and it's showing the progress and eventually says it's successfully installed. Now if I check the status again, we see the CSV package. Here is a schematic of the architecture of a package manager. Normally, the package manager has to maintain some kind of database or indexing system to manage all of the packages included in that package manager. The actual package themselves, they are probably stored in somewhere else. For example, some kind of store location. In order to install or remove packages in the user space, the package manager program has to interact with the central indexing or database repository in order to get the up-to-date package information. And based on this information, then the package manager program can go back to the storage location to retrieve the actual package. Once the packages are installed, they can be organized into several environments. For example, there may be some default environment, but the user can also create additional virtual environments. Each different package manager system has its own way to create such virtual environments, but all of the package management system seem to have this capacity in order to deal with the runtime situation. At the runtime system will load one of the environments in order to execute a package. Even if you are only executing one single package, because of the dependency relations to other packages, this one single package may still have to access other dependent packages. So therefore, in each of this environment, even if you are installing only one package, normally there are multiple packages that are installed under that virtual environment. There are several components that are involved in terms of organizing Julia's packages. The first part here is the central repository that stores all of the public open source registered Julia packages that is hosted on GitHub under the Julia registry GitHub organization. The second part is a bunch of GitHub repositories hosting the packages themselves. And this is where the authors of the packages maintain their packages. GitHub or Git is probably the most popular tool in terms of keeping track of changes. And Julia uses this mechanism extensively for package management. Some of the popular packages are organized into the so-called GitHub organizations based on the application areas. For example, as displayed here, BioJulia is one of the organizations that contains a number of packages related to computational biology. Another example is Julia Data that organizes a number of packages related to data manipulation and I/O operations. There are also a bunch of many other individual repositories. They are directly hosted under the author's individual GitHub accounts. The third part of this structure is on the local computer. Typically, Julia programs is installed somewhere else on the file system. For example, in my case, the Julia executables is installed under a location under my home directories. This location is separate from the other location I'm going to talk about. The Julia packages are typically installed under this .julia directories under the home directories. This directory can be configured to be something else, but typically this is the default setting. Under this .julia directories, there are a bunch of other subdirectories. One of the subdirectories is registries. And under the registry directory, you will see that if you go there, it is a copy of the central general registry. So here you also see a bunch of subdirectories, A, B, C, D, E, F. These are actually the copy of these A, B, C, D subdirectories from the master repository. So these are the different components that we will talk about when we talk about package manipulation or management later in this talk. So keep in mind that the data are coming from, the indexing data is coming from the general registry, where the package itself, the files and etc., they are coming from the actual repositories storing the package themselves. And on your local system, the local system will make a copy of the package or the indices from the general registry into your local system. And so these different places are being updated at different times. So every time we run the package manager will automatically try to synchronize itself with the master registry to synchronize the database. And also, if you are updating the packages, it will also check whether each individual packages have available new versions appears in their corresponding repositories, and then the system will automatically sync up your local repositories with the remote, the hosting sites. Let's look at what Julia's general registry look like. So on GitHub, there is a Julia registry organization. In this GitHub organization, one of the repositories is general. So this is the place where Julia stores the general registry. So if you look at this repository, you will see a bunch of directories named by the alphabets letters. And then you will see one of the important files is this registry.toml file. If we click on this file, you see that there are a few lines of metadata about this file, followed by a description, and followed by a bunch of packages. So the packages, the format of the rows begins with some kind of hash code, followed by the name of the package names, followed by the path. And this path refers to the subdirectories we just saw. For example, for this package, the name starts with the R. It is stored under the R subdirectories. And for the second row, the package name is KCPJLL, start with the K, so it is stored under the K subdirectories, and so on. And if you scroll down all the way to the end, you will see that at this point, there are like 5,000 plus packages registered in the Julia's general registry. So these are all of the packages registered. And if you look at the description here, you will see that it has a very generous policy. Basically, it will accept any package submission that follows the general guidelines. So if you have a package and you are ready to share with the community, then you can follow the submission procedure. Then eventually, if your package name is unique and you go through all of the steps, your package will eventually appear as one of the entries in the Julia general registries. And when that is the case, then other people can install your package by using the PKG mechanism that we have seen. Next, we will look at several examples of GitHub organizations that host some of the popular packages. One of them is this FluxML machine learning library. In this organization, there are 33 packages currently. One of the popular ones is flux.jl. As you can see, a typical name for Julia's package is has the extension .jl. And there are also several other important packages inside this organization. Another one is Julia Linear Algebra. In this organization, there are 20 plus packages related to numerical linear algebra. Some of them are actually quite famous. For example, the ARPack is one of the famous package that has a long history in numerical computing. Another organization is Julia Parallel. So this is an organization that hosts a number of packages related to parallel computing. For example, the famous MPI library. So MPI.jl is Julia's interface to the MPI libraries. And there are also several other famous packages. Another organization is this JUMP organization that hosts a number of packages related to numerical optimization. Some of the packages are actually quite famous. Currently, there are 41 packages. One of the important properties or features of the Julia Package Manager is that each version of a package is installed exactly only once. There are no duplicates on the system. Then different environments were used from this unique set of installations. For example, in my Julia folder, there is a subfolder called packages. Under the packages, there is one of the packages is this data frame package in this example. If I look into this folder, I will see that there are 3 installations. And if I look at the project file in these installations, I will see that there are 3 different versions installed here. So for example, if one of my virtual environment requires data frame 1.0.1, that virtual environment will use installation from this folder. If the other different virtual environment also need the installation of data frame of 1.0.1, that second virtual environment will also pull from these unique installations. So basically, for 1.0.1 on my system, there will be only one single installations. And this is different from other package manager systems. And the same thing applies to these other versions. So if you look into this packages folder, you will see a number of different packages, but then you know that every version of each packages is only installed once. Julia uses a file called project.toml to maintain the package information for the project environment. For example, the default environment that exists when we enter the package mode is stored under this folder. So under the Julia directories, there's an environment folder. Underneath, there's a serious version corresponding to the Julia's version. And underneath, there's a project.toml. So this is the project file that maintains the environment for the default environment. In addition to this default environment, a user can create arbitrary environments to organize different kind of project combinations. For example, you can create additional folders that has its own project files. You can create another folder that has a different project files, and so on. And so in the next slide, we are going to look into the project file and to see its contents. What are in a project file? So to answer this question, let's look at one of the project files associated with one of the versions of data frame package. So I am looking at the .julia folder under my home directories. So there are several layers of subdirectories. So the top layer is the core packages. Underneath, there are a bunch of packages. Data frame is one of the packages, but there are also multiple versions of data frames on my system. So I'm looking at one of them. Underneath this folder, there is a file called project.toml. So this is the content of that file, project file. The first line of the file is the name of the project, name of the package. And also there is a UUID, unique code associated with this package. And also there's a version number of this package. This is the 1.0.2 associated with this folder, and there are other versions installed under the data frame folder. After the first section, the second chunk of the contents are the dependencies, the depths. So all of these guys are the dependency packages that are required by the data frame package. So here the format is the name of the dependent packages, and the other information is the UUID of those dependency packages. So each of these dependency packages has their own folder, and in that folder there is also a project file, and this is the UUID in their corresponding project files. So these are all of the packages that are dependent of this data frame packages. So when data frame is installed, all of these packages with the corresponding versions will be also automatically installed onto my system. The next chunk of the information is compatibility information. So here, the data file specified the version ranges that are compatible with this current version of data frames. So for example, some of these packages, they are required to be within certain version ranges that are determined to be compatible with the data frame packages. So normally the developers of the package, for example, in this case, data frames, they have to determine the range of compatibilities, and they will put the information here. So with this information, when you install the data frame packages, the system will automatically determine whether the system can be successfully installed, depending on whether your system have these other packages in the version ranges. And further down, there are some additional informations, also package name followed by UUID, and we are not going to talk about details here, but just know that this file basically specifies all of the information that are required to successfully install the data frame package in terms of their compatibility and also all of the dependency information. Next, we will see how to manipulate the project environment, including how to create the environment and add packages to the environment, and how do you develop or modify a package inside the environment, and also how to update an environment. Here, I'm going to demonstrate how to create a virtual environment in Julia Package Management System. Suppose I am in one of the arbitrary folder, so in this case, one of the temporary folders, and then I run the Julia command, and then we enter the Julia repo system. So we see the logo and then the version information. Now, inside the Julia repo, I press the square bracket key to enter the package mode, as we did earlier. When you do that initially, you see that the command prompt has changed to the package mode, and also it shows that we are in the default environment. So from there, I'm going to run the command activate tutorial. Activate is a command to activate a certain virtual environment. Tutorial is the name of our current virtual environment. So this is an environment I'm creating. So activate tutorial will perform the following action as indicated by the message here. After we run this, the system says that we are activating a new environment at a certain location. And this location is my current directories. And under the current directories, it will create a new folder. The name of the folder, tutorial, is the name of my virtual environment. And then it will place a new file, project.toml file, underneath this virtual environment folder. So this is what the activate command does. After that, I can run the status command. And before that, notice that now after the activation, my package mode command prompt has also changed. Now it is showing the new name, new environment I'm currently in. So before it was a default environment. Now since I have activated the tutorial environment, I am now in the tutorial virtual environment. So here, when I run the status, it will show me that this environment setup is according to the project file. But at this point, the project file is empty. And this is because I have activated the environment and it has created the project file, but I have not added any Julia packages into this environment. So therefore, the project is empty. It exists, but it's empty. So now in my virtual environment, I'm going to add one package to my environment. In this case, the name of the package is called example. And actually, this is one of the registered Julia package. This package usually is only for tutorial purposes. It is not really a useful computational package in Julia. So by adding this package example, you will see the following thing happens. So initially, at the very beginning, you see that it's updating the registry. So the general registry on my local computers are stored under the .julia folder, as we mentioned earlier. So before you do anything, the system is trying to synchronize my local registry with the remote central location, the Julia's central registry on the GitHub repository. Make sure that I have the latest general registry. After that, it is resolving the package versions and is updating my project file. So before, my project file is empty. Now it's updating because I have added one package to my project. So this file will be updated. And also, since this package will trigger other dependencies packages, another file called manifest is also updated. Now, after this is done, when I run status again, now the project is not empty. It now contains only one package, and the package is called example. And this is the version of example that it's installed by this add command here. So at this point, the folder tutorial contains only two files. One is the manifest file, one is the project file. So at this point, the packages example has been installed. So suppose now I want to make changes to the package example. So the way to do this in Julia is to use the develop command under the package mode. So when we say develop local example, this means that we are going to make changes to the example package. This will basically make a Git clone of the entire repository onto the local folder. So when you run the command, you will see a bunch of messages. So it's cloning from github.com, the original repository of this package example, and it's updating several things in my local project and manifest files. because you are making the modifications, so it's automatically incrementing the package version by 1. So initially the package was 5.3, now it's 5.4. After this action, when you check the local folder, you see that in addition to the 2 files here, the tutorial folder with this originally 2 files, as we saw earlier, now there is a new folder called the devel. Under the devel, there is an entire clone Git repository for this example package. And all of these files are cloned into this dev subfolders. So at this point, you are ready to make changes to this repository, to this package. Now, suppose we use our editor to open this file, and notice that we are opening the file under the dev folder, because this is the entire clone of the example package. So we open this file, example.jl file, and this is the original file. And suppose we add 1 line in this file. So this is before the change, this is after the change, and we save the file. So now this file is modified with this new line. And so this file, this Julia file that has defined several functions. And what I'm doing here is to add another function definitions. So this function does not exist in the original file. And now I have added this new function in the new file. So after the change, when we import this module example, and now this is modified, so Julia detected the change, and now Julia is a compile language, so it's recompiling the source file. And after the recompiling, now we can load this function. The +1 is the function that I just added into the file, and now we can execute this function. And from our previous screen, we know that this function will basically add 1 to the argument. So when we pass +1, 5, the return value will be 6. When we call the function with the argument 10, it will return 11. Right? So this is an extremely simple function, but it's to demonstrate that Julia does respond to the change by recompiling the program and then execute the function accordingly. So at this point, if you run the status command, it will show that we are at version 5.4 and corresponding to the package under the deb folder. And so at this point, you can maybe commit the change and to basically keep the change you want by committing it to the Git repository. Or suppose we are done with our experiment and we want to return to our original state. And the way to do that is to use the free command. And so we registered example to be under the deb environment so that we can make changes and to do experiments. The free command is to do the opposite. So now we can free the example package from the deb environment. So when you do this, you will see that it is again updating the project and the manifest files and is restoring from 5.4 back to 5.3. So this was our original state before we launched the devel command. One powerful feature of Julia's package manager is to let you add unregistered packages. In this example, we are still in the tutorial environment, and when we run the status command, we confirm that we have only one added package. This package has been registered at the registry, so it has a version and it has a name. Now, suppose you want to add some package directly from some author's account on GitHub. So you can do so by adding that package's GitHub web address. So in this case, you are adding the HTTP github.com/the author/the package name. So when you do this, it will basically pull that package from GitHub and then add the package into your local virtual environment. So as you do that, it will also try to check the registry at the general registry. And so after this, you will see that your project and manifest are both updated with this new added package. So after this point, if you run status again, you see that in addition to the original example, which you had before, now you have this new package. And this new package, instead of a version number, in addition to the version number, it also has this URL or the web address that is the address of where you pull the package from. So if we look a little bit closely at the manifest file, after we added this unregistered package, we notice that in addition to the original registered package, which is example, this unregistered package is added. And the format is slightly different from the typical registered package. So for example, the URL of the GitHub web address is also recorded. When you install a package, you do not always have to install the latest versions. For example, for whatever reason, suppose you want to install a particular version of the package. For example, for data frame package, I want to install 1.0.0, which is not the latest, but for some reason I want to this particular version. You can do that by using the add syntax. So in addition to just add data frames, you can specify a particular version, and this version will be installed. And you will see the typical output messages. And because this particular version will trigger a different set of dependencies, so you will see that all these additional dependencies will be installed. And at the end, it will report that it has been successfully installed, and also with some statistics number, right? So all of these dependencies depend on this one particular version. In summary, we have talked about the architecture of Julia's package manager and also the actions you can do with the package manager. In terms of the architecture, it consists of the central registry, which is essentially a database that stores the metadata of all of the registered Julia packages. The system has a very inclusive submission policy. So anybody who has a Julia package, as long as your naming convention and other criteria are met by the submission policy, you can submit your package and that will be registered in the central registry. After that point, other people can discover your package and probably install your package for their computations. Normally, a Julia package is hosted on GitHub as an open source package. The repository can be a standalone repository under your GitHub account, or it can be under some GitHub organizations. An organization is something about one particular application domains that we have given some examples. And one thing I didn't talk about is that you can also set up a private registry. The central registry, general set registry, is an open source public one on GitHub, but it is also possible to set up your private registries. And essentially, the system is using these two files within a package, a project file and a manifest files, to control the dependencies and compatibility information. And as long as you maintain this in your package, then your package can be safely used by other people, and that will guarantee the compatibility and dependencies. With this package manager system, we have also demonstrated that you can add or remove or update or develop your packages within the Julia package manager. And also one interesting feature we pointed out is that each version of a package is uniquely installed on the system. So there will be no duplicates on your system. So the installation tree tend to be quite clean and well organized. And also, as a user, you can create arbitrary environments for any combination of packages. As long as they are compatible, you can create arbitrary environments for different situations for your computations. Earlier in the talk, we have also reviewed the OS level package managers as well as the user space package managers. In general, the OS level package managers, they are for general purposes and they are not targeting at scientific computing. On the other hand, domain-specific user space package managers are useful for providing packages that can be conveniently installed for scientific computing. We have also looked at the general architecture among all of these package managers, and they share some common architecture, although the details differ. Now we have reached the last slide of the presentation. In general, Julia's package system is quite flexible and powerful. Here are some additional links, including Julia's language documentation and also the PKG systems documentation that you may want to check out if you are interested. This concludes my presentation. Hello, so are there any